So the next part we are going to start looking at is liquid-liquid extraction. Let me just share the slides. Okay, so if you think about what liquid-liquid extraction does, you have an aqueous phase or an organic phase. In this particular case, let's say you have an aqueous phase containing some solute, that is, say, component P in this particular case. It is this P that we want to extract out from the aqueous phase. So these kinds of situations come across in many of the pharmaceutical industry where you have a component in the aqueous phase, or let's say you are making some kind of a drug using fermentation. So fermentation is in the aqueous phase, right? So you put your water, you put your sugar solution, you put the um, uh, you put all these nutrients, and then you inoculate with a certain organism, and then the organism grows and makes this particular product. So at the end of the fermentation, what you have is your pharmaceutical compound in an aqueous phase. Along with this, there are many things like your like all these metabolites that are secreted by the organism. Microorganisms themselves are there, sugar is there, so many things are there. Let's just simplify and we say that this aqueous phase now contains some compound P which we want to extract from the organic phase. So what you do is you put your organic phase, so this could be a solvent or it could be some specific extractant along with the solvent. We will see those kinds of extractants little later. But the solvent and P, now you agitate, you make a dispersion. So you have created a dispersion. You disperse the organic phase, let's say this yellow phase, in the aqueous phase, and the aqueous phase is continuous phase, organic phase is dispersed phase in this particular case, but you can have it other way around as well. So you could have an aqueous phase dispersed in an organic phase as well. So what happens is now the P gets transferred from the aqueous phase into the organic phase, and an equilibrium is reached, and then we settle these two phases. So we get back our organic phase. Now the organic phase contains P, but the aqueous phase also contains some of the original P that has that is partly remaining behind. So we reach an equilibrium of P in the organic phase and P dissolved in the aqueous phase. Do you agree with that? If you have any doubts, you can always ask. Now this equilibrium, once it is reached, then I can take out samples from the aqueous phase, organic phase, and we define partition coefficient or a distribution coefficient. So that KD, we denote it as KD, or D, distribution coefficient. We denote it as concentration of P in the organic phase divided by concentration of P in the aqueous phase. So if you want to depict it graphically, if you do this kind of experiment, you do multiple such experiments, either change the solvent ratio of the aqueous to organic, or you change the initial amount of P that is there in the organic phase. And if you do such experiments and again every time measure the concentration of P in the organic phase and concentration of P in the aqueous phase, so let's call it as P aqueous and let's call this as P organic, and you will get a set of points, and we can draw a smooth line, or we can draw we can fit a relationship, and the slope of this line would be our distribution coefficient. So that's our slope of the line, right? It's passing through origin, so the slope and the value at either this and this, P organic divided by P aqueous, y by x, because it is passing through we are showing origin here. So the slope and the value at any point, the ratio of the two values y and x, they would be the same. So we call this as a distribution coefficient. Now if you want to extract P from the organic phase, would you prefer a high KD or a low KD? Would you prefer a high KD or a low KD? Any thoughts? High KD, yeah, well, Right. You want high KD because you want more of the P to come into the organic phase, and therefore you would prefer a KD or a D which is as high as possible. But remember, next thing, what are you going to do with this P in the organic phase? What are you going to do with this P in the organic phase? How are you going to purify this P? So what is the subsequent step in purification of P? That also matters. If you are going to back extract into an aqueous phase, then you don't want a very high D, because then your back extraction into another aqueous phase would be hampered. But let's say you are going to now um, evaporate this organic material and now do a cooling kind of crystallization for crystallizing out P, then you will prefer very high distribution coefficient. Or another words, you would select a solvent which will give you a high distribution coefficient. We'll again look at some of the solvents a little later. What kind of solvents we should choose. Okay, so thermodynamically, you have seen that if I want to write an extraction, write an equilibrium of P in both the cases, in both the phases, at equilibrium, what would I write? How would you write it from thermodynamics point of view? Any thoughts? Right. So if you want to write, you will say that x of P in the aqueous phase, gamma of P in the aqueous phase, and fugacity of P, the pure form, would be equal to x of P in the organic phase, gamma of P in the organic phase, and f of P in the pure form, right? And then the f of P in the pure form would just cancel out from both sides. So that's how you have been writing in your thermodynamics course, how the equilibrium between the of P between the two phases is described. So if you want to write now the equilibrium constant, or K or KD, whatever way you like to call, people call it as D, people call it as KD, whatever you like. I mean, different people use different nomenclature, but that's okay. You can stick to one nomenclature. So let's say KD. If I write from this relationship now, KD would be equal to what would I write? KD would be mole fraction in the organic phase divided by mole fraction in the aqueous phase would be equal to gamma of P. In general, we are writing for any solute I, because now we are going to look at more than one solute also. Maybe we have more than one component being generated in the aqueous phase, so we might want to look at different components getting extracted. So if you write for any component I, xi in the organic phase divided by xi in the aqueous phase would be equal to gamma I in the aqueous phase divided by gamma I in the organic phase. That's coming from here. Just take this ratio, right? Now, if you have a dilute solution, then you can always write concentrations in terms of mole fractions, right? Do you agree with that? Concentrations you can write in terms of the mole fraction. See, mole fraction is nothing but concentration of the component I divided by the total concentration. Total concentration. Say, for example, if it is water, total concentration would be, if its density is 1000 kgs per meter cube, total concentration would be 55.5555 kilomoles per meter cube. That's the total concentration. Now, if the component is very dilute, let's say fermentation processes, components are very dilute, then this total concentration would just be nothing but molecular weight of the solvent. This total concentration would just simply be density divided by the molecular weight, right? So remember, 1000 divided by 18, if it is for water, then it is like 55.55, right? So this xi we can replace in terms of concentrations, and now we can write a proper distribution coefficient as concentration of I in the organic phase divided by concentration of I in the aqueous phase, and you will find that you get this kind of relationship, right? You must have seen this in your thermodynamics course last year. Okay, so if you think about this now, the activity coefficients, if it's a dilute solutions, we can even write it in terms of the infinite dilution activity coefficient, right? Remember, if it's a dilute solution, then these gamma i's we can replace as gamma I infinity in the aqueous phase, and gamma I in the organic phase can be replaced by gamma I infinity in the organic phase. Now, reason for writing this gamma I infinity is many times we have very dilute solutions. For example, if you are thinking about let's say pesticides that are there in groundwater, now they are at very low concentration, few ppm level, and therefore they are really at an infinite dilution. The mole fraction is practically tending to zero. So either if it's at a higher concentration, you can write in terms of the actual activity coefficient, or if it's at a dilute concentration or concentration, you can write it as in terms of the infinite dilution activity coefficient. Now, one of the ways in which we look at the kind of solute that we have, so the distribution coefficient is dictated therefore by nature of the solvent, nature of P that is present, and the water. How much the water likes P or how much water dislikes P is decided by this activity coefficient. How much P is liked by the organic solvent, how much P is disliked by the organic solvent is decided by this activity coefficient of P in organic phase. So if, let's say for example, P, our solute, water does not like it, then the gamma I infinity would be very large. And if P is liked by the organic phase, then this gamma I infinity would be small, and this ratio would be very large. So if it is hydrophobic solute, if P is a hydrophobic solute, that means water does not like it. Water tends to throw away the P as soon as it sees any organic. So then the distribution coefficient would be very high. Whereas if it is hydrophilic, then the distribution coefficient would be very low, right? So these are the extreme cases that we are talking about. So one of the ways in which we characterize how this P behaves, whether it behaves in hydrophobic manner or a hydrophilic manner, is by finding out its distribution coefficient in a known organic solvent. And the known organic solvent that we take for this particular purpose is N-octanol. So N-octanol, C8 alcohol. So you have C8, 8 carbon atoms, and OH. So C8 alcohol, it's called as N-octanol. So we find out its the distribution coefficient of this particular solute P in octanol and water, and then it is called as octanol water partition coefficient, or you can call it as a distribution coefficient between octanol and water, and it is denoted as DOW, right? And if you use the molecular weights and densities of water, so this particular case it is water, this is water, and this is organic solvent, that is octanol, right? Density is 827 kg per meter cube, molecular weight is 130 for octanol, density is 1000 kg per meter cube for water, molecular weight is 18. So you can get this directly in terms of, you can substitute these values and you will find that the DOW, octanol water partitioning coefficient, is equal to 0.1145 or 115 into gamma I infinity in the aqueous phase divided by gamma I infinity in the organic phase. So this octanol water partition coefficient tells you how hydrophobic the solute is, right? It is just a matter of convention that octanol is taken as a representative organic sample, but really distribution coefficient is a ratio of the concentrations in the organic phase and concentrations in the aqueous phase. And when you write these octanol water partition coefficients, you can find out that these numbers can be very large. The values of D can be very large, or they can be very small. So it could be of the order of thousands, or it could be of the order of 0.01, 0.001 of that order. So we don't talk in terms of just the octanol water partition coefficient. We rather talk about log to the base 10 of octanol water partition coefficient. So people write it as log to the base 10 d octanol water or log to the base 10 k octanol water. So if the value is negative or very small, that means this is KOW or DOW would be 10 raised to minus 0.1. Whereas if the value is very large, let's say 5.31 here for this particular compound, KOW would be 10 raised to 5.31. So you can see how hydrophobic this hexachlorobenzene is as compared to, let's say, acrolein. Acrolein would be very hydrophilic as compared to octanol, as compared to hexachlorobenzene. And these values you can find for many compounds reported in the literature. Just tells you how hydrophobic or hydrophilic that compound is, helps you to select what kind of solvent I should take for doing liquid extraction. Now another thing is that when we talk about these, now you might have heard in the news or you might have read in the newspapers, there is a big hue and cry about pesticides being present in water. So you see some of these compounds, these are pesticides that are commonly used in farms. And so I'm just using the word pesticide as a general word, but it could be a very specific pesticide. It could be a herbicide, killing the herbs that are there, herbs in the sense killing the unwanted plants, weeds that are there, or it could be a fungicide, it could be killing the fungus, or it could be a pesticide like rats and things like that, or it could be an insecticide, so insects that come on the plant. So depending on, I'm just using the common word agrochemicals or common word pesticide for that, but it is these are very specific compounds for very specific diseases or pests that trouble the crops. So you must have heard that these pesticides are present in the groundwater and they are ending up in the food chain. And if you are eating fish or if you are eating non-veg food, then these pesticides would be consumed by the animals or fish, and these pesticides would get enriched in the fat that is there in those fish or meat or whatever. And so fat being an organic molecule and a hydrophobic molecule, the KOW value is also a very much indicator of how much pesticide enrichment or pesticide accumulation would happen inside these animals or inside the fat or inside the fish or whatever. So that's another use for this KOW, that you can quickly estimate the amount of pesticide that would get accumulated in these animals or in the fats of these animals. So that's how we decipher whether the solute is hydrophobic or hydrophilic. Okay, let's go forward now. So what we will try to do is we'll do some kind of calculations based on this distribution coefficient now. You might have done some of these calculations in the organic phase, sorry, not in organic, what I'm saying. You might have done some of these calculations in your undergraduate course, but doesn't matter. It's just a still quick review. So suppose there are now two components, A and B, in the aqueous phase, and we want to extract any one of them. Let's say A is our desired one, B is our undesired one. So we use an organic solvent, we extract them. Now both of them reach an equilibrium. So A reaches at equilibrium, B reaches at equilibrium. So the distribution coefficient of A we can define, distribution coefficient of B we can define, and we can define a separation factor. We can define a separation factor like we define for distillation. We define in distillation, what do? We have an aqueous phase. Sorry. In distillation, what do? We have a liquid phase and we have a vapor phase, right? So we say XA and YA, XB and YB. So if it's just a binary, what do we say? How do you define alpha AB? Relative volatility, you say it is YA by XA divided by YB by XB. The volatility of A divided by volatility of B. That's how we define our relative volatility. And if it's a binary, this YA by XA, YB is simply 1 minus YA and XB is simply 1 minus XA. You recall that? So higher the relative volatility, easier it is to separate A and B by distillation. Same way, now for liquid extraction, we could define separation factor alpha AB as a ratio of the distribution coefficient of A divided by distribution coefficient of B. So higher the value of alpha AB, the easier it is to separate A from B using liquid extraction, just like distillation. Okay, let's quickly revise something about ternary diagram. So what you have is, we have seen little bit of ternary diagrams in our distillation course as well. Let us quickly discuss here as well. Now, if you think about this, so we have water as this vertex, the organic solvent that you have taken as this vertex, and P, the solute that you are trying to extract. And we have seen that this, everything under this blue curve is a two-phase region. So this is a two-phase region. And this is a homogeneous region, single phase. And we have seen tie lines as well. You must have seen in your undergraduate course as well. These are the tie lines. So concentration of P and concentration of P in the organic phase. So this is P in aqueous phase, water rich phase. So aqueous phase and organic phase, organic solvent rich phase. So these two concentrations that are there in equilibrium, that they are joined by a tie line. So if I have this particular concentration and if I add the organic solvent, let's say I add 1 mole or 1 liter of the aqueous solution having this composition and 1 liter of the organic solvent, then I will reach somewhere here, midpoint of the line joining this particular point and the organic solvent point. And then this particular point goes through the tie lines. So, and it's in the two-phase region. So it will split into two phases, the aqueous phase, water rich phase, and the organic phase, the solvent rich phase. And the concentration of P in the water rich phase would be this much, would be given by this point, and the concentration of P in the organic phase would be given by this particular point. So we have seen all this. Now, question that I want to ask is, how would the ternary diagram look like for a very good solvent for P, right? This is, let's say, solvent, organic solvent 1. Now suppose an organic solvent is better than this for extracting P. How would the ternary diagram look like? That's the question that I am asking. So just take a couple of minutes, think, and then tell me the answer. Right. So if you have a better solvent, our two-phase region, let's say our ternary diagram, so water, solvent, and P is here. Now look at this here. This point is far away from this side of the triangle. That means it still contains substantial amount of water. If you look at this, this is like 10% water is present in the organic phase, right? So instead of having a binary system of water and P, now we have made two ternary systems. One organic phase still contains a lot of water, and now you see this point, let me just rub this out. This point is still far from this the side of the triangle, it still contains maybe 3-4% of the organic solvent. So ideal system would be that I have the two-phase region, the blue line. Let me take that color, the blue line. The blue line should be practically touching this side of the triangle. The blue line should be practically touching this side of the triangle, so that there is no water going in the organic phase, there is no solvent going in the aqueous phase, and this two-phase region should be as wide as possible. So it is as if you would want the two-phase region to be equal to the whole triangle itself. Now, if your tie lines are like this, then you can say that, oh, practically no organic solvent is there in the water phase and practically no water is there in the organic phase, right? Obviously, this doesn't happen when you go to large and larger concentrations of P. But if you are having dilute solutions, then it is good to select a solvent that would have the two-phase region practically coinciding with the side of the triangle, right? So you would want a two-phase region which is practically coinciding. Let's take this blue color again. So you want the two-phase region to be practically coinciding with the side here. You want it to practically coincide with the side here. And then it may even do something like this. That's okay. But as long as you are working in this region, then you can essentially neglect the mutual solubility of solvent in water and water in solvent. Solvent solubility in water, that's in the aqueous phase, and water solubility in solvent, that's the organic phase. So you want to minimize the water solubility in the organic phase, you would want to minimize the solvent solubility in the aqueous phase, right? If that is the case, then you can treat it like a binary system, isn't it? You can treat it like distillation, vapor and liquid, or you can treat it when you like the case you were doing when you were doing gas absorption. Do you remember what you did in gas absorption? Do you remember what did you do in gas absorption? You had a gas and you had a liquid. So your gas, let's say, was air, and some ammonia was there in the air, and you absorbed that ammonia in water. So in the air, which means we have nitrogen and oxygen, what did we consider? We only considered ammonia solubility in water. We did not consider vapor pressure of water in the air phase, gas phase, nor did we look at the solubility of nitrogen and oxygen in the water phase, isn't it? So we could treat it as if there is only one solute, ammonia in this particular case, that is at equilibrium between the gas and the liquid. So that can happen only if your the two-phase region is the sides of the two-phase region are practically along the side of the triangle and you're at a dilute solution. Remember, same thing we did here when we were talking about the binary system. We were writing the thermodynamic equilibrium. This organic phase, you can take it as a practically solvent if it's a dilute solution, and water. So we wrote this organic phase in terms of molecular weight of the solvent divided by density of the organic phase, and molecular weight of the aqueous phase and density of the aqueous phase, that is water, right? That's how we got this 0.1145 or 115 nearly. Okay, so if that is the case, then whatever we have done with respect to gas absorption, same thing we can do for liquid-liquid extraction. Let's